The last time we talked about the cosmological perturbation in the regime of the general relative theory. We derived the conservative equation and the perturbing equation by using the Einstein field equation. So the results is the following. For the conservative equation, we can obtain the linear version of the continuities and Euler equations from the partial mu of the thrust annotation T menu. Then the perturbing quantity like as the delta rho, delta p, and the velocity anisotropy stress satisfies the following continuity and the Euler equation. And we can obtain the equation of the motion for the energy density by studying that the anisotropy stress is 0 and the perturbation of the process can be related still with the energy density by using the speed of the sound, Cs. Then then we can obtain the equation of the motion for the energy density perturbation delta rho only. And today we'll talk about how can we simplify such a complicated form of the density perturbation by using the two limit. The first one is a Superhoizon limit, which means that the distance scale or momentum scale is larger than the Hubble. And second, we'll talk about some specific initial condition, so-called adiabatic perturbation. So before that, let's determine which components of the universe will be discussed for the cosmological perturbation. There are two components. The first one is the matter, and the other one is the radiation. For the matter does not have the pressure, so the quantity related to the pressures all equal to the 0. So the continuity and the Euler equation that reduces the following simplified form. And by combining them, we can obtain the equation of the motion for the matter perturbation delta m. And the new terms in the right hand side includes the dependence of the matrix scalar potential capital pi and psi. So now let's consider that the Superhoizon limit. So which is before that the Superhoizon limit, let's talk about the subhorizon first. So for the subhorizon case, the distance scale is smaller than the Hubble inverse. Equivalently, the K mode is extremely larger than the Hubble parameters. Then this means that we should remain their scale because the K mode is larger than the Hubble scale, but during this approach, the gravitational potential is almost static, so that we can remove the time derivatives of the potential in the right hand side. But before, instead of that, we can ignore the Hubble's term. Then this is for the conservation equation for the subhorizon limit, and if we consider the 0 components of the Einstein field equation, then this is reduces to the following form. And if we insert this one, which is the form of the Poisson equation, then we can obtain the ungrown equation for the matter perturbation. And this result is consistent with the Newtonian approach. Now let's turn to our focus apply the Superhoizon limit, which is the scale distance scale is larger than the Hubble inverse, so equivalently the K mode is extremely smaller than the Hubble scale. Then the partial gradient is strongly surplused compared to the time derivative, so that we can ignore all the Dal scales term. For example, in the Euler equation, we can remove the del psi. Then the solutions are simplified there. For example, the Euler equation, the velocity of the matters that decompose with the h to the minus 1, where there is a scaling factor here. And also for the continuity equation, because the nabla terms, their terms can be ignored, so the delta m prime is just 3 times of the time derivatives of the scalar potential. So that this means that for the superhorizon condition or outside of the horizon, the evolutions of the matrix density perturbation delta m is purely determined by the time dependence of the matrix perturbation capital pi prime. Similarly, we can obtain the equation of the motion for the radiation perturbation because the radiation has a relation between the projects and the density with the factor of 1/3. So the continuity equation and Euler equation that reduces through with some specific factors. And by combining them, we can obtain the equation for the density perturbation for the radiation. And if we impose the superhorizon, then all the gradient term can be reduced. Then just the remaining term is the radiation perturbations are also determined by the time derivatives of the matrix perturbation or scalar potential capital pi, but the different one is just the coefficients that change its the bow compared to the matrix perturbation. It's because the different equation of the state for the radiation. So for the superhorizon limit, we can obtain the matter perturbations and radiation perturbations predetermined by the just evolutions of the scalar potential capital pi of the matter perturbation. And if we integrate this differential equation, then just the difference point is the coefficients and the integration constant for the matters and the radiations respectively. But at this time, there are no specific condition for this constant. These constants are really independent. But for the adiabatic modes, these initial conditions impose the relation between these two constants, the Cm and the Cr for the matters and the radiation. And for the adiabatic condition, all the components share the same local time shift delta t. So the perturbations of each component for the each component delta rho I corresponds to the uniformly scale over the background evolutions of the rho bar. So this condition can be expressed through with the light years of the delta rho over the rho bar, for each component is all identical. So the this can be written by using the background continuity equation. Then for some specific component I, the density perturbation delta I over the 1 over the W I, where W is the equation of the state. These quantities are all the same for each component. So we know that the matter component has the zero equation of the state, and the radiation component has the 1/3. So the for the matter, it has the 3 over the delta m, and for the radiation, it has the no 1 over delta m, and for the radiation, it has the 1 plus the 1/3. So the relation between the matter perturbation delta m and the radiation perturbation has some factors of the 3 over the 4, which is arising from the equation of the state of the matters and the radiation for this adiabatic condition. So now we can obtain the simple relation between the delta m and the delta L in the adiabatic mode. Also, there are some other initial conditions, so-called isocurvature perturbation, The Earth curvatures are defined by the difference between the quantity delta I over the 1 plus Wi for the component. And for the Earth curvatures perturbation, these uh, quantities that are constant. And if the universe follows this curvature perturbation, then this influence some specific signatures in the CMB anisotropy, and the current observations that constrains this curvature perturbation strongly. And in addition, for the inflation model, several models generalize the adiabatic initial conditions, so we'll focus on the adiabatic perturbation rather than the isoculture perturbation. So under the such as Superhoizon limit and the isoculture perturbation, now we can simplify the complicated forms of the density perturbation. So for the zero components of the Einstein field equation, we'll revisit this one. For the Superhoizon limit, the K mode is smaller than the Hubble scale, so all the gradient term can be negligible, so that the first term, the R scales capital pi goes to 0. And also we will set the anisotropy stress is evident, so the psi and the capital pi's are the same. And during the Superhoizon limit, the pi prime is the almost static. So this regular component equation that is existed in the following form. And by using the Brodmann equation, the Hubble term can be reconciled with the in terms of the radiation and density, so that we can obtain the relation between the radiation perturbation and the scalar perturbation during the radiation dominant era. So if we obtain the evolutions of the scalar potential, then we can obtain the radiation perturbation. So the evolution of the potential can be obtained by the other components of the Einstein equation. Let's focus on the trace path of the IJ component. In the Newtonian gauge and Van Exelman isotropic stress, this equation reduces in the following form. And by using the 0 Einstein field equation again, the left-hand side can be rewritten by inserting that. Then the equations are following. And by using the first and the second Friedmann equation again for the Hubble prime and the Hubble, then the equations are simplified the following form. And for the Superhoizon limit, also the gradient term can be negligible. And the Hubble terms that follows the following time relation for the constant equation of the type W. Then by using the only this differential equation, we can obtain the solutions in the two independent solution. And this is represented by the equation on the side W. And the second terms are just correspond to decay mode, so the important one is going mode, and the gravitational potential remains just a constant for the Superhoizon limit, just at this term. Maybe there are some strange point for this relation. Oh, I see. So we did not determine the constant CR here. So the delta R radiation perturbation and the scalar perturbation follow this relation. And in this case, we can define the new quantity, so-called curvature perturbation, which is the gauge invariant. because the equation of the state W, the changes when the universe transitions from the radiation dominant to the matter dominant. And this modifies the evolutions of the matrix potential capital pi. So the we need to define the gauge invariant quantity, which is the independence of the universe error. The gauge invariant quantity is the curvature perturbation, the Xi and the curly R. They are transformed the following for this component. So the and if we use the some specific relation, this is the continuity equation for the background, and this curly hours the constant slope for the radiations and the matter dominance error. And we can evaluate this Xi and R. So the for the Xi, and for the Superhoizon and the radiation dominant error, delta follows minus 2 capital pi. So the Xi can be written in terms of the matrix potentials and the equation of the state omega. So the relation between the Xi and the scalar potential capital pi has a factor which is represented by the equation of the states omega W. And for those, again, we can use the Einstein equations again. And combining these two equations, just the Hubble times the velocity is the same term with the Xi. So the Xi and the R's, curly R's are the same for the Superhoizon Q. So this is just the same with the curly R. So the relation between the curvature perturbation curly R and the matrix scalar potential capital pi has just a relation with some specific backtest, which is composed by the equation of the state W. And the curly R's are just a constant over all the approach of the universe, but the capital pi is the changes. So if we insert the equation of the state for the RD, W equal to the 1 observed, then the relation between the capital pi and the curly R has a factor of the 2 over 3. And for the matter dominance error, W is equal to 0, so the relations are following. So the pi's changes over the cosmic history when the universe transits from the RD to the MD, but the curly R's are just very constant. So there's the 9 over the 10 factors when the universe transits from the RD to the MD for the scalar potential. So today we talk about some simplifications of some complicated form of cosmological perturbation and the general relativity theory by using the two inputs, the condition, the first one the Superhoizon limit and the other one is the adiabatic perturbation. For the Superhoizon limit, we can drop all the gradient terms in the equation, and in this regime, the density perturbations are fully determined by the evolutions of the matrix perturbations, partially the scalar potential capital pi. And if we impose the adiabatic condition, then the relative perturbation of the radiation and the components is a fixed with the common sharing times shift, and this leads to the relation between the radiation perturbation and the matter perturbation with the specific axis. And by using the Einstein periodic equation, the radiation density perturbations is strongly related with the gravitational potential capital pi, and we can define the curvature perturbation curly R, which is the constants when the universe transits from the RD to the MD, and this can be related with the capital pi. So we can obtain the binary result, the relation between the radiation perturbation and the matter perturbation, and relates to the metric perturbation and the scalar perturbation for the superhorizon and the adiabatic perturbation during the RD. So if we determine the evolutions of the gravitational potential capital pi, then we can study all the evolutions of the radiation and the matter perturbation, very simple process. And in the next time, now I turn to the some specific examples of the evolutions of the matrix perturbation. Um, there are several limits already we discussed: superhorizon, subhorizon limit, and the universal transit from the RD to the MD, and for each K modes um, the going start movements of the growings are different. So we'll discuss it in the next time.